Disentangled representations and attribute manipulation in fashion. Attribute-specific subspaces for image manipulation retrieval, outfit completion, and conditional similarity retrieval. Another video right now on disentangled representation and attribute manipulation. You can subscribe on each post. Each video has its post on my website. You can subscribe by mail at the end or on an entire blog. You can find other posts as well. You can subscribe on YouTube. I assume that you see this video on YouTube. Alright, so I do these videos on useful things, useful overviews of things you can do with machine learning. So right now we have this task for an image. Give me a product from database, which is, it's a shirt, and it's a shirt same shape but different color, right? Long sleeve, same cut but different color. How would you do that? As well, there's related task. You have this fashion outfit and you would like to add one more item into the outfit, and we will actually find out that in this particular case this task will benefit from disentangled representation. So how is disentangled representation related? Well, entangled representation means that we have representation of the data, for example image, but we don't know, there's no special direction in which we can go from the vector. There's no special way how I can modify the vector such that I would modify values, some sort of inner attributes of the product. And disentangled, on the other hand, actually each set of attributes have a separate dimensions, and we can say that it's fully disentangled if all underlying factors have separate dimensions, which I think that's I don't understand how you could 100% do it, but yeah, never mind, let's go. So here we have this visualization that you have image, and you have, for example, a ResNet representation here, and then you train two-layer networks to separate category, color, and pattern, and then you are able to manipulate them. So this is a supervised way, but we will start with talking about unsupervised disentangling methods. So you definitely know about variation autoencoders, right? You have this encoder and decoder, and you have latent space in between. And in general, actually, there's this, let me speculate a little bit, some disentanglement, I think, in this architecture, which is known, you've probably seen it. I think it happens because you compress into low dimension and a small space at the same time. That's, the regularization term, sometimes it's called. And that forces that you will get only high level factors, and because it's small space, the same value for high level factors has to be next to each other, so it sort of forces disentanglement a little bit. It's sort of high level how I see it. In general, there are specialized methods for forcing disentanglement. So you sort of reduce mutual information between the latent variables, between the latent dimensions, and or total correlation, and this leads to unsupervised disentanglement methods. Because by reducing the correlation, we can expect, okay, we will get some kind of latent things, but are those really those useful things? I will answer that soon. So then you have GANs, but in case of GANs, you still need some encoder and decoder to get some latent space somewhere. And then you can do this as well with flow-based models. For example, I have this post on OpenAI's GLOW, which is a flow-based model. It's actually an interesting area of research, these flow-based things. So they are basically a little bit like a variational autoencoder, except they have some several special properties, and their decoder actually is reverse of the encoder, because in this case, in the flow-based models, you can calculate reversal. They are reversible. And the latent space is forced to be independent Gaussian factors, and that's exactly what we mentioned here, at least how I understand it. In case of variational autoencoders, if you force some kind of total correlation, it's basically like the flow-based model. And we can see as well results of the flow-based model, right? So the problem here, I will mention below that you don't, by default, you don't know which directions are which, right? You cannot force exactly the dimensions to align with what you would expect. So you need to have additional data, and then, for example, you can find on the latent space of faces of people, you can find a general vector from along which we go if you modify an image representation. In that direction, you can add a smile on a woman's face, right? Okay, so here on the left, we have a source image. We modify it on the latent space by center direction, and we can generate, then we reverse the encoder and we generate a smiling photo. All right, so let's go. Unsupervised disentangled representation. Right, so as I mentioned, there are various methods, but there is this challenge. There are these challenges. There's this paper published, it's ML 2019, which mentions does large-scale overview to sort of experimentally support the theorem, which says that because there is no way to know what is the true latent representation, and there are infinite transformations, you will never get exactly the true distribution as you would imagine. Right? So you may reduce into the right number of dimensions, right? But you may get this uncorrelation, but you won't know which direction is what. You cannot force the composition. There may be some rotations on the latent space. That's how I understand it. They trained it on this interesting data set called Shape3D, which has these simple scenes which have 10 dimensions: object shape, object size, camera rotation, and colors of the object, floor, wall, ceiling, and so on. 10 dimensions, and none of the methods were able to reliably decompose these 10 dimensions exactly. There's always some kind of transformation because there are infinite of them. So basically what they say that all is not lost, but you probably need to add some assumptions to actually get the right decomposition on the latent space. Or I think if you have additional data, you can search for the right directions on the latent space. So basically you need to have some kind of supervision a little bit because you are adding some information about the data, right? So it's not going to be fully unsupervised. Okay, there's one related topic called MultiTask Learning, and recently Google on NeurIPS 2021 released this method for grouping tasks together. This is a meta-learning approach, such that if you have a set of tasks, then it may be possible that if you train some of them together, you will get better performance on all of them. But the tasks have to be related. If that's true, you can gain better performance. And how do you know they are related? They define this intertask affinity, which correlates well with overall performance. And basically, it's a measure of one task's gradient, how it affects loss of the other task. And if it affects it positively on small set, you can then say it will be beneficial to group these tasks together. So here's an image of the process. So you input image to the key points. Okay, I'm not familiar with the first step, but then you have the second step. You calculate intertask affinities using these gradients effects on the losses. That's supposed to be some relatively cheap calculation. Once you know that, you can group the tasks together. Right, and the tasks they have here are segmentation, key points, edges, normals, depth, and what they found out that in this example is that segmentation, edges, and depth should be together trained, and then these normals and key points should be trained separately together. All right, and actually I will soon note that this outfit recommendation actually seems to be improving on disentangled representations, and that may be the case of the good multitask learning affinity. All right, so supervised disentangling. So I mentioned unsupervised disentangling methods, and now I will talk about supervised disentangling, and which is also related to this multitask learning. So in Amazon 2021 paper, Learning Attribute-Driven Disentangled Representations for Interactive Fashion Retrieval, which is sort of on some of the fashion tasks. You know, these fashion tasks, they are not exactly, you know, place where the biggest brains spend their time, you know, to win the state of the art. But it's sort of interesting. All right, so this so that means that it's not very hard to be state of the art in this area. Okay, supervised disentangled presentation learning. All right, so what we have here is that we have this image of a product. We get embedding, for example, this one could be ResNet or AlexNet, and then we let me zoom a little bit. All right, and then we do this multitask training, and as a result, we will get embedding, which is explicitly separated into three parts. One is just embedding of the category of the product, one is embedding of the color, and one is embedding of the pattern. And they are composed like this, and at the same time, I also store prototypes of embeddings of those discrete value attributes. Right, so for example, for each color, I have specific embedding, and then I can do this word to vec operation, minus red plus blue, and I will modify the color. And you can search like this. All right, so what's the architecture exactly? So as I mentioned, there's backbone network, and then for each attribute, I have fully connected two-layer network, which maps into attribute-specific subspace. And I produce image attribute embedding, right? Embedding for category or color and so on. And this means that I will get this entangled representation. That's the topic of the video. So they call this attribute-driven disentangled encoder. They have in the architecture as well this memory block, which stores prototype embeddings for all values of the attributes. So for example, each color has one prototype embedding. So memory block is over here, down here. And what they force, they optimize block diagonal elements to be non-zero, but non-block diagonal elements to be zero. Means that the color representation prototype vector should have zero to other attributes like category or pattern, right? They in general use triplet loss, and they have several losses. The loss function is really quite complicated. Let's spend a little more time on this image and explain the loss function again. So yes, triplet loss means that they have three inputs, three different input values, three different products, and they have several losses. So they have labeled triplet loss. So representations with the same labels have to have same vectors, right? So that means that if I have triplet loss of three products, two of them have black color, one of them has red color. So the representations with the same color have to have the same vectors in that section. And all in general, if they have all the same attributes, they have to have some representation. There is consistency triplet loss. So attribute representation of so consistency loss is that I have those prototype vectors, right? So if I have a red color in that image, this is supervised, so I know, I have this image with the red color, so I want its corresponding embedding to be close to the prototype vector. And compositional triplet loss. So this one makes sure that I can compose different prototype vectors and get I get close to the right representation. So I do this by I create manipulation vectors. So I'm minus red plus black, and I'm checking that I'm getting the right black attribute embedding. And I have memory block loss, as I mentioned, of block diagonal goes to 0. So this memory block which stores prototype vectors makes sure that those dimensions that don't correspond to the prototype of the attribute needs to be 0, close to 0. So what kind of experiments they ran? So they have shopping 100k deep fashion, around 100 samples of both, a couple attributes, and then they train those several losses, and they then test this attribute manipulation retrieval downstream. The top k accuracy. Yeah. So so first we need to as well to compare to previous approaches. So there is this AMNet. That's so this previous approach, it has no disentangling, and they have something like prototype vectors, but instead those prototype vectors actually represent sort of like a command. So they create these prototype vectors represent command. Okay, replace color with red. That's the command, and they have neural networks which takes the image, takes the command, and tries to produce the right output vector. Then there is this FSN, which is attribute representation with localizations for flexible Flash search. This one instead finds the places in the image which represent the attribute within the image, and then they use weighted pooling on the earlier layers of the convolutional layers to get more of the essence of that embedding, and then they use this approach to produce those to modify the image and so on. In this experiment, we use AlexNet as backbone network for comparable results from the previous methods. And we also have ablations showing that adding all losses in the model is best. So basically, if we look at this, AMNet top 10 accuracy 25, FSN 38, and DDE is 41. So this 41 top 1 accuracy is winning over here on shopping 100k. So that's why I said that this paper is state of the art on this task. Okay, so I promised this output completion. How would you do that then? So they base their idea on previous research. They use ResNet 18, and there's the same architecture as CSA-Net, which is also from Amazon 2020. And basically, they take the disentangled representation, they add some feed fully connected layers on top, get the representation. Then they also, take, I have this image, and I know which is the category in, and I would like to predict some target category. So they have this one-hot encoding of input category, target category. They pass it through fully connected layer and create attentions. These attentions are then applied on the results of those embeddings, of those specialized embeddings, and we get a ranking clause for recommendation. How do they then do this for entire outfit? So you have so instead of having just one product, I have a collection of products. I would like to know how well this item goes together with that. So instead, very simple, instead of just having one loss, how well it goes together, I take average of that product with all of the products in the outfit and get the ranking clause. And then I train this with some triplet loss on negative pairs as well. All right, so that's it. You can subscribe by mail on each of the posts on the blog, and as well you can subscribe on YouTube. And let me know if you notice some interesting paper, some interesting area where I could make some useful video about it, how to use it as well. Okay, so thanks a lot and continue to learn, and hope to see you next time. Bye bye.